in the future. All right, so all right, so now the YouTube is on. So let me whoops. Mute that, minimize that. Okay, so let me also minimize this. And let me do this. Okay, so now we're going to get into the actual electrochemistry part of this topic. So as I said before, there are two types of electrochemical reactions. You have one type where an electric current is generated by a spontaneous reaction. And then the other type is where we use an electric current to drive a non-spontaneous reaction. So we're going to look at the first type of reaction and talk about all the different details concerning that. So what you're looking at here is what is called a galvanic cell, all right? And this is basically what is used to create an electric current based on a redox reaction, based on a spontaneous redox reaction. So let me try to describe what we have here in this particular example of a galvanic cell. We have two solutions in two separate beakers, right? One solution is a solution containing zinc sulfate, the other solution containing copper sulfate, copper 2 sulfate actually, right? Immersed in each solution are electrodes. So in the case of the solution to the left, which is zinc sulfate, a zinc electrode is inserted and a copper electrode is inserted in the other solution. And also inserted into the solution is this U-shaped tube here, which connects the two solutions, right? This consists of a material known as agar gel, which is soaked with potassium chloride, and it's called a salt bridge. And I'm going to explain the role of that shortly. Another thing I want to point out is that the electrodes themselves, right, will be connected by an external circuit, which consists of copper wires. And as a part of that circuit, you have what is known as a voltmeter. And the voltmeter is used to measure what is called the potential difference between the two beakers here, all right, containing the two solutions, all right? So this is what happens when this is set up. What happens is that you have over on the left side, this reaction taking place where the zinc is converted to the zinc ions as a result of oxidation. So in other words, the zinc atoms will lose electrons to form the zinc ion. And those electrons will enter the external circuit, as you can see here, all right? So that is basically what is happening on this side here. Now, on the right side, the copper 2 plus is undergoing reduction by gaining 2 electrons to form copper. So the electrons that are entering the external circuit will encounter the copper 2 plus here, reduce the copper 2 plus according to this equation, and as a result, you're going to have the formation of copper solid being formed, right? So basically, what you'll be having simultaneously occurring in both of these vessels is that the zinc will undergo oxidation. So therefore, the zinc anode here will lose mass, and the copper electrode here will gain mass because copper will be formed as a result of the copper 2 plus ion gaining electrons to form the copper solid, all right? So basically, you're going to have a redox reaction taking place where the oxidation is taking place in the beaker on the left, and the reduction is taking place in the beaker on the right, and the electron transfer is taking place as a result of the electrons being lost here, entering the external circuit, and ending up combining with the copper 2 plus to form the copper solid, right? So we can write half equations representing what is happening in each beaker, and then the net equation, of course, is the sum of this equation and this equation, which will be this equation right here. So this is basically the equation describing the overall redox reaction that is taking place, all right? So that's basically a very simple, or one of the simplest examples of what we call a galvanic cell. And just to add some additional terminology here, this is called a half cell, the combination of the solution with the electrode dipped in it. So this is a zinc sulfate solution with the zinc electrode dipped in it. That combination is called a half cell. And this is also called a half cell. And the combination of these two, the two half cells coming together, where you have them connected as shown here, where you have an electric current flowing from one half cell to the other, we call that a cell, all right? So basically the two half cells come together to form a whole cell. Now, let me explain the role of the salt bridge right here as I described before. As I said before, this consists of an inert material known as agar gel, which is soaked with potassium chloride. Now, this is very important in order for the current to continue to flow in the external circuit. Now, the reason why that's important is because as this oxidation reaction takes place, you're going to have a buildup of zinc ions in this solution here. And if the concentration of the zinc ions becomes too great, then eventually what will happen is that the electric current is going to stop, all right? So in order to facilitate the continuous flow of electric current, the zinc ions will move up into the salt bridge and be replaced by the chloride ions, which will be moving into the solution in order to maintain electrical neutrality in this particular half cell. And similarly, in the case of this half cell here, where copper 2+ will be converted to copper, eventually, if we do not replace the copper 2+ ions, what will happen is that the current will stop as a result of the depletion of the copper 2+ ions in this solution here. So basically, what will happen is that as the copper 2+ is being converted to the copper, potassium ions will move from the salt bridge into the aqueous solution on the right side, again, to maintain electrical neutrality, all right? And therefore, the electric current will flow, continue to flow, all right? So that's basically the role of the salt bridge. Some other terminology that I need to talk about, which I probably should have mentioned before. So over here where oxidation is taking place, we call that the anode, right? So the anode is where oxidation takes place, all right? Whereas on this side where reduction is taking place, we call that the cathode, right? So you'll always have oxidation taking place at the anode and reduction taking place at the cathode. So the next slide is basically describing what I talked about in terms of the role of the salt bridge. So as I said before, in the case of the cathode, there will be a buildup of zinc ions as the zinc is converted to zinc ions, and therefore the zinc ions will move up into the salt bridge and the chloride ions will move simultaneously into the solution. And then as far as the anode is concerned, where, well, actually, I think I have the terms confused here, right? So actually, hold on. Oh, yes. So in the case, right, this should be, hold on, wait a minute. Okay, so I just realized there's an error here. This should be the anode here, right? So where it says for the cathode, that should be for the anode, and this should be for the cathode. So please make a note of that on this page right here, all right? So here, for the cathode, reduction of the copper 2+ will take place. And as I said before, that would result in a depletion of the copper 2+ ions. And basically, the result would be that the potassium ions will move into the solution and the sulfate ions will move into the salt bridge. Okay, so that's basically the role of the salt bridge. Okay, so we can actually measure the potential for the electrons to flow through the external circuit between the two half cells. And that measurement of that potential is given different terms. It could be called the cell voltage or the electromotive force, which, to be perfectly honest, is a bit of a misnomer because there's no force that is literally involved, but it comes out of this belief that existed before that there's a force that exists which pushes the electrons along the circuit. But that's now known not to be true, but the term still survives its literal meaning. And then another term, which is more often used in most textbooks, we call it the cell potential, which is basically a more accurate representation of what is taking place. the cell potential basically measures the potential for the electrons to flow from the anode to the cathode, all right? So we can measure it. We can use an instrument known as a voltmeter, which is what is used here. And in this particular case, for the half cell or for the cell that we were looking at, we can measure that difference, and it turns out the difference will be equal to 1.10, provided that the molarities of the solutions are 1 molar each, right? So as I said before, this is the equation for the reaction, right? The zinc is undergoing oxidation by giving up its electrons to the copper 2+, and you end up with this product. So we can represent the reaction using this redox equation. But there's another way that is used to represent what is happening here, specifically as it relates to galvanic cells. And it looks like this, all right? Now, as I said before, the concentrations of the copper 2+ and the zinc 2+ will be 1 molar. So we use what is called a cell diagram to represent this cell. So this is what it looks like, right? So this here, you see the symbol for zinc, and it gives you the state, which is a solid that represents the electrode, the zinc metal that is dipped in the solution. And then we have zinc 2+, 1 molar beside it. That's a solution of zinc ions itself. And then we have 2 lines like this, which basically shows a separation between the half cell for the zinc on the left, and then for the half cell for the zinc on the right. You'll notice that you have the copper 2+ symbol here, 1 molar beside it, and then a line, and then copper solid, all right? So we call this a cell diagram. And you need to pay attention to the order of how these things are represented, because you'll notice that we put the zinc here, right, solid, then a line, and then zinc 2+ 1 molar. What this is indicating is that the zinc is being converted to the zinc 2+. In other words, oxidation is taking place. So this is called the anode, right, where oxidation occurs. And then on the right side, you'll notice that you have copper 2+ here, and then the line, and then copper solid. So this side here is showing that copper 2+ is being reduced to the copper solid, and therefore we say that is reduction, and this is called the cathode, which is where the reduction occurs. So that's basically what we call the cell diagram, which is a shorthand way of representing how the cell is put together based on the composition of the 2 half cells, all right? Now, it would be nice if we could make a measurement of the potential, the absolute potential of 1 half cell. Unfortunately, we cannot do that because in order to measure the potential of 1 half cell, we have to hook it up to another half cell. And therefore, the only thing that we can really measure is the potential of 1 half cell in relation to the other. So to overcome that issue, what was decided by the powers that be is that we define what is known as a standard half cell. And the standard half cell is basically what is seen here on the right in this diagram. We call that the standard hydrogen half cell. Let me check something here. Okay, so let me skip this page for the time being and show you this diagram here. This is basically what the standard hydrogen electrode or half cell looks like, all right? And as you see, it's also abbreviated, known as SHE, standard hydrogen electrode. It consists of hydrogen gas being bubbled into a solution of hydrochloric acid. And it doesn't have to be hydrochloric acid. It could be any strong acid, but hydrochloric acid is the usual suspect used in this sort of setup. There's an electrode here, a platinum electrode, which is basically an inert material which is used to allow for the electrons to go into and out of the solution and into and out of the external circuit, right? So basically, the powers that be decided that this would be the standard by which all other electrodes are measured against in terms of determining the standard electrode potential. So basically, the definition, by definition, the EMF or the electrode potential for the standard hydrogen electrode is defined as 0, all right? So we define that as 0, and therefore when we hook this up to any other half cell, then basically whatever the potential difference between the SHE, the standard hydrogen electrode, and the half cell would be considered to be the measurement of the electrode potential of that half cell, all right? So I just thought I should show you that first so that I can show you on the previous slide what it looks like when you connect the standard hydrogen half cell, which is this right here, to the half cell for zinc in zinc sulfate, right? So this is the zinc half cell right here, which is also the zinc electrode, and this is a standard hydrogen electrode. And of course, we connect them by an external circuit, which also has a part of it, the voltmeter, which is used to measure the potential difference between those two half cells, right? So basically in this particular case, what was found was that the zinc electrode is where oxidation will take place. So this is the oxidation half equation for the zinc electrode. And then for the hydrogen electrode, this would be the reduction half equation. So when you add these two together, you're going to end up with the net equation, which is this right here. Now, for standard conditions, right? If you remember, we talked about standard conditions for enthalpy, for free energy, for entropy. The conditions would be the same for electrode potential, right? So the temperature would have to be 25 degrees Celsius. The concentrations of anything in aqueous solutions would be 1 molar. If they're in the gases, the pressure would be 1 atmosphere, right? So those are the standard conditions that are set. And based on those standard conditions, we can determine the standard electrode potential, all right, for the particular element or for the particular half reaction. So I don't see it here. Let me see if it's on the next page. In the case of, okay, here it is. So in the case of this setup here, it was determined that the standard value for the voltage, the standard voltage, would be 0.76 volts, right? That's a measurement. If you were to set this up and you read off the measurement from the voltmeter, that is the standard voltage. So basically the way we determine that is that the standard EMF or the standard voltage would be, by definition, the difference between the standard EMF of the cathode minus the standard EMF of the anode, all right? So first you have to define or determine which is a cathode and which is the anode. The cathode is where reduction takes place. The anode is where oxidation takes place, right? So in the case of this setup here, for this cell, that's the equation. And because reduction takes place at the cathode, right, we put that first, and that is defined as 0. And for the anode, where oxidation takes place, we don't know what that is, but when we measure the difference between the two, then we find that E of the cell is equal to 0.76, as we said before. And therefore, since this is 0, that means that the standard EMF of the zinc electrode would be equal to minus 0.76. And that's how you determine the standard EMF of the zinc electrode, the zinc half cell, all right? So that's basically how that is determined for zinc. And basically, this is how you determine the EMF of any half cell. You determine that by hooking it up to the standard hydrogen electrode, and then you determine if, in which one you have oxidation, in which one you have reduction, and then you apply this equation to that to determine which is the cathode, which is the anode, and then based on that, you can determine the standard EMF of that particular half cell. So here's another example. Oh, by the way, so for the reduction potential, we call it also the reduction potential because we're talking about the potential for the reduction reaction to take place. The reduction reaction, of course, in the zinc half cell is the zinc 2 plus 2 electrons to give zinc, right? And that would be the equation for which the reduction potential would be what you see here, which is minus 0.76, all right? Okay, here's another example, again, to illustrate how this works. Now, in the case of hooking up a copper half cell where you have copper metal dipped in a copper 2 plus solution, hooked up to the standard hydrogen electrode, what you'll find is that in this particular case, it's the copper 2 plus electrode where reduction will take place, right? So therefore, this would be the cathode in this case, all right? In the case of the hydrogen electrode, oxidation is taking place here, so this would be the anode, all right? So basically, this is the anode where oxidation will take place. This is the equation for what takes place in the cathode. So therefore, and also let me just say that when this is set up, it was determined that the EMF of the cell is 0.34 volts. Now remember, by definition, the standard EMF of the cell is always going to be cathode minus anode in terms of their respective potential values. So since the EMF of the cell is 0.3 volts, 0.34 volts, you're going to put that here. For the cathode, that would be the copper 2 plus combination electrode. So that's E0 for the copper 2 plus copper. And for the standard electrode, as far as the hydrogen electrode is concerned, that is 0 for its reduction potential by definition. So therefore, when we put 0 here, then we determine that the standard EMF reduction potential for the copper electrode is equal to 0.34 volts. All right. So that's basically how we determine the EMF of the copper electrode based on it being hooked up to the standard hydrogen electrode. Okay. Any questions concerning what we just discussed with respect to determining the standard reduction potentials? Any question? All right. So if there are no questions about that, let me move on to the next slide, which shows you a table of different reduction potentials for different half reactions, right? So please note that the name that is given to all of these, they're called standard reduction potential. And that's because they're giving a measure of the potential of these reduction reactions taking place, these reduction half reactions, right? And in fact, a more comprehensive table is given in Canvas. So let me show you where that is. So let me go here and let me go to files. Let me close this out. And oh, you know what? Let me see here. Okay. Let me go to, let me see here. Let me go to tables. Okay, tables. And then, okay, so here it is. Standard reduction potential. So when I click on that and download that, okay, this is a rather large, well, actually 4 pages, right? So this gives you different half equations and their standard reduction potentials, right? And if I remember correctly, this table, let me see here. Okay, table 3. Table 3, table 4. Oh, okay. So the first table gives you the standard reduction potentials in terms of their values, starting from the highest to the lowest. And then down here, they gave the same thing, but in alphabetical order in terms of the substances involved in the reaction. So they both contain the same values, but they have different arrangements. The first one in terms of the magnitude of the electrode potentials, and the second one in terms of the alphabetical order of the substance undergoing reduction. All right, so you can use one or either to do any type of calculations involving standard reduction potential. Okay, so I just thought I should point that out. So whenever you're doing any problems in this chapter, this is the table that you're going to use. The values from this table is what I expect you to use in order to solve problems of the type that we're going to see shortly. Now, going back to this page right here. So as I said before, this is a list, not as comprehensive as the ones I showed you before, but there are certain comments I want to make concerning standard reduction potential. The first of which is that the standard reduction potential is for the reaction as written as a reduction, right? So all these reactions here and the ones that I have shown you in the tables located in Canvas if you look at all the half reactions, they are written as reduction reactions, all right? And the corresponding reduction potentials are provided for that. Another statement which is true, and this will become important when it comes to doing certain calculations, the more positive the standard reduction potential, the greater the tendency of the substance indicated to be reduced, right? That important fact will become very important when we do certain calculations. The next thing I want to say is that half-cell reactions are reversible, right? However, if it reverses, then the sign of the standard reduction potential changes, right? So for example, if you take this first one here, where fluorine plus 2 electrons gives you 2 fluoride ions, the value for the reduction potential for that is 2.87. Then the reverse reaction would have a negative 2.87 value, all right? And then the other important point, which might seem a bit confusing, but it's actually true, changing the stoichiometric coefficients in the half-cell reaction does not change the value of E0, which is a reduction potential. In other words, if you were to, for example, again, using the fluorine example for the first one right here, if you were to divide right through by 2, it does not change the E0 value here. The standard reduction potential will still be 2.87, all right? So that's also something that will become important when it comes to solving some of these problems, all right? Okay, so let's look at this example here based on what we have just discussed. So the question is here, what is the standard EMF of an electrochemical cell made up of a cadmium electrode, which is dipped in a 1 molar solution of cadmium 2 nitrate solution, and a chromium electrode dipped in a solution of 1.0 m chromium nitrate solution? Okay, so the way we'd go about this is that we would go to the table and look up the reduction potentials for each of these half reactions, right? So for the cadmium 2 plus being converted to the cadmium, you go to the table and you see that the standard reduction potential for that is minus 0.40 volts. And then you look up the same value for converting the chromium 3 plus to chromium. Now, what I would do if I were you is write down the half equations in each case. In the case of the second one, when you look up the EMF value, the reduction potential value, that is equal to minus 0.74 volts, all right? Now, if you compare these two, you'll see that the one with the higher value will be the cadmium half cell, right? Minus 0.40 volts is obviously of a higher value or more positive compared to minus 0.74 volts. So what does that mean? That means that when you hook up these two half cells to each other, the reduction reaction is more likely going to be this reaction right here, and this reaction here is more likely to reverse. So basically, this would be the result. In the case of the oxidation, which would be the reverse of this reaction here, the equation is going to be this, and the EMF for the reverse reaction is going to be positive 0.74 volts. This is more likely to remain, so that would be the reduction reaction. So basically, you just simply rewrite this down here, all right? And then what we do is that we add these two equations together. Now remember, when you're adding two equations together, the number of electrons lost and gained must be the same. So basically what we do is multiply this equation by 2 and multiply the second equation by 3. But remember, multiplying this by 2 and multiplying this by 3 does not affect these values. It does not affect the EMF values, right? So therefore, all we have to do next is add these two equations together. And of course, the electrons will cancel out and you write down what remains. And that means to get the EMF of the net equation, we add these two values together. And this would be the standard EMF value for this particular cell made up of these two half cells. All right. And that's basically how that is done. Another way of setting this up or writing this down is basically using this definition of the EMF of the cell that we saw before. The EMF of the cell will be equal to the standard EMF of the cathode minus the standard EMF of the anode. Now, in this case, you have to be careful because you have to figure out which is a cathode and which is the anode. So the way you do that is that you look at each of these values. The one that's more positive would obviously be the cathode because that's where the reduction is more likely to take place. So therefore, the standard EMF of the cathode would be the minus 0.40, and the standard EMF of the anode would be minus 0.74. So therefore, you put them in the equation here, minus 0.40 minus 0.74, and that would be equal to 0.34, which is the same result as we got here. So you can take this approach, you can take this approach, but this one, I would say you have to take real care because if you're going to take this approach, you have to identify which is a cathode and which is the anode. And the one that's a cathode is the one that has the higher standard EMF value, the one that's more positive, because that's the one where reduction is most likely or more likely to take place. All right? Okay, any questions about this particular example? Any questions?
If you do the second way, using that formula, would you still have to do the whole canceling out of the electrons?
No. No, you don't have to. I mean, and it looks easier, but like I said, you have to be careful, right? You have to identify the cathode in this setup, which is the one with the higher EMF value, which is minus 0.40 compared to the minus 0.74. So, you know, be careful. That's all I can say when you're doing it this way. It looks easier, but you can make the wrong choice. All right. If you, you know, I remember when I was learning this for the first time, my preference was actually doing it this way because when you lay it out this way, at least for me, when I lay it out that way, you know, it's kind of straightforward to me. And I remember when I was learning this and trying it this way, I keep making mistakes. I keep putting the wrong numbers in the wrong place and so on. But now I'm better at it with more practice. So, you know, it's up to you. You know, if you do it this way or this way, it doesn't matter to me, to be perfectly honest. All right. Okay. Any other questions? Any other questions? Okay. So let me see what next is coming up. All right. You know what? Let's take a break here. It's now 11:47. So this time, since we were cut short the first break, I'm going to extend this break by 3 minutes. So this is now 30 minutes to 12. So we're going to get back here at 12 o'clock. All right. Okay. So I'll see you then. Okay, folks, I am back. All right, so hold on 1 minute. All right, so let's talk about the relationship between standard reduction potentials and some other quantities that we're familiar with. And what you're going to see is that there's a relationship between the spontaneity of redox reactions and the standard EMF. Now, let me just introduce to you this equation which relates the free energy change of a reaction, of a redox reaction occurring in a cell to the EMF of the cell. So this is the equation right here. Delta G is equal to minus N times F times the EMF of the cell. Now, N is the number of moles of electrons that are transferred in the reaction. So this underscores the importance of having a balanced equation which indicates the number of electrons being transferred. F is a constant which is known as a Faraday constant, and it represents the amount of charge that is carried by a mole of electrons. So that's a constant value, by the way. It's equal to 96,500 coulombs per mole, all right? So that's Faraday's constant, and that will be important later on, as you're gonna see. So this is, and E, of course, would be the EMF of the cell, which is measured in volts, right? So therefore, you can just basically plug the numbers into this equation, and that gives you the free energy. And this equation is basically the same as this, with the exception that this is specific with respect to standard conditions, right? So if the conditions are standard, and if you remember, the standard conditions would be, 25 degrees Celsius temperature, 1 molar solutions, pressure of gases would be 1 atmosphere, then basically this equation would apply to that particular situation. So let me also introduce you to this equation here. Now, this equation relates the standard free energy of a reaction, again, reduction reaction, to the rate constant. And this is, I'm sorry, not rate constant, the equilibrium constant. And this is something that we met before, all right? Basically, we talked about the fact that the larger the K value, the more negative the standard delta G value, and as a result, the more spontaneous the particular reaction is. Now, it turns out that this is also, because of this equation, this expression will be the same or equal to this expression right here. And therefore, we can rearrange it to get an expression for the standard EMF of the cell, which is equal to RT over NF times ln K, all right? Now, if the conditions are standard, in other words, if the temperature is 25 degrees Celsius, which is equal to 298 Kelvin, then, and of course, R is a constant, F is a constant, then basically we can put those numbers into this equation. R is equal to this here, 8.31. T is 25 degrees Celsius, which is 298 Kelvin. And of course, F is, as I said before, the Faraday's constant, which is equal to that. You plug all those values into this equation, then you come up with the following, which is this equation right here, right? And because of the relationship between ln K and log K, this equation becomes this equation. So these two would give the same results if you plug in the value of N and K into either of these equations, you're going to get the same value of the standard EMF of the cell, all right? So this shows you the relationship between the rate, I keep saying the rate constant, the equilibrium constant and the standard EMF of the cell, all right? So to summarize the relationship between the K, the standard EMF, and delta G, we can use this diagram right here, right? So to get from delta G to K or K to delta G, you can use this equation right here. To get from delta G to the standard EMF or vice versa, this is the equation you would use. And finally, if you want to get from the standard EMF reduction potential to K, you can use this equation here or vice versa, all right? So it all depends on, the kind of question, what you're given, and what the question is asking for. Okay, so the next slide is basically a summary of the relationship between delta G standard, K, and the reduction potential or EMF of the cell. So basically, if delta G is negative, based on this equation here, and based on a negative sign here, if delta G is negative, that means that K is less than 1, all right? If K is less than 1, then ln K would be negative. Well, let me see here. If K is greater than 1, I'm sorry. If K is greater than 1, then minus RT ln K would be negative, which means that delta G standard will be negative. If K is greater than 1, that means that the standard EMF of the cell would be positive. And what that means in terms of the relationship between the products and the reactants in a reaction, a redox reaction, basically the reaction favors the products, all right? Now, if delta G is 0, that means that K is equal to 1. That means that the standard EMF of the cell is 0, which means that the reactants and products are equally favored. And if delta G is less than 1, that means that the EMF of the cell, I'm sorry, if delta G is positive, that means that K is less than 1. Again, based on this equation. If K is less than 1, ln K will be negative, delta G would be positive, and therefore the standard EMF of the cell would also be negative as a result, and therefore in this case the reactants would be favored in this case, all right? So that's just basically summarizing the relationship between these thermodynamic quantities. Okay, so based on what we have just covered, let's look at this example. So you're given this equation here, and the question is asking for you to calculate the equilibrium constant based on what we have covered so far. So, of course, you can identify this as a redox reaction, right? Now, in order for us to determine K based on what we have learned so far, the equation that we would use would be this equation right here. This equation relates the EMF of the cell to the equilibrium constant. So if we can find the EMF of the cell, and if we know what N is, then we can rearrange this equation to find K. So how do we do that? Well, firstly, we need to identify the half equations that would add together to give this equation here. So one half equation would be the conversion of silver to silver plus, which would be this right here. And then the other half equation, which is a reduction half equation, would be the conversion of Fe2 plus to Fe, which would be that half equation right here. So once we establish the half equations, we see that the number of electrons being transferred would be 2. 2 electrons being lost here, 2 electrons being gained here. So that 2 would be the end value that we would put right here. So at least we solve, for now, that part of the problem. The other part is determining the EMF of the cell. Now, the EMF of the cell would be equal to the difference between the standard EMF of the oxidation and reduction potential. Remember, it's always reduction minus oxidation. Now, what that means is that we'd have to consult the tables to look up the EMF values of both half cells, right? For the silver and the iron half cells. So when you look it up, you'll see that the iron half cell would have a value of minus 0.44, and the silver plus the silver would have a value of 0.80. And because this here, let me see here. Okay, so this is the way I would do this particular problem. So hold on 1 minute. For the reduction potential for the iron half cell, I have a sneaking suspicion these numbers are not correct. So let me do a quick check here. Let me go to the tables. Hold on 1 minute. Let me quickly go to the tables because I have a sneaking suspicion that something is off. Let's see. Tables, where are you? Okay, there are tables. And then let me look up standard reduction potential. Let me download that. Okay, so in the case of the Fe2 plus, okay, Fe2 plus to Fe, when I looked it up, hold on, let me, hold on. I hate when this happens. Hold on. Okay. Okay, I'm sorry about that, folks. Let me go back to where we were before. Okay, so that's where we were. Okay, so when I look up the Fe2 plus to Fe, that gives you minus 0.44. So this would be for this reaction is going to be 0.44. Oh, minus 0.44 volts. Okay, and then now for the silver going to, hold on, where is it? For the silver plus going to silver, the value I see here is plus 0.8 volts. Now this is the reverse, so this will be minus 0.80 volts. So, okay, so it works out to be the same. All right. So basically, when you add these two equations together, you're going to get minus 0.80 volts minus 0.44 volts. So basically, it's the same result. Okay. So basically, you're going to take, hold on. Sorry about this again. Okay, so basically, we identified this as the iron half cell will be where the reduction takes place. So that's a cathode, so that's minus 0.44 volts. And then you minus from that the value for the oxidation or the anode half cell, which would be 0.80. I just looked it up and I confirmed that this is correct. So therefore, when you work this out, you're going to get minus 1.24 volts, which would be the answer as far as the electrode potential when you connect these two. So the next step is to find K, which is what the question is asking for, all right? So to find K, we have to go back to this equation here and rearrange it to solve for K. And when you do that, this is what you're going to end up with. And then you plug the numbers in. You have the standard EMF for the cell here, which will be minus 1.24 volts times N, which is going to be equal to 2. And then you do the rest. And according to my calculation here, the answer works out to be equal to 1.23 times 10 to the minus 42. So that's basically how you do that particular problem. All right? Okay, any questions about this particular examples, I'm sorry. Any questions about this particular example? Okay, so let me move on now to talking about another important equation, which is derived from some of the things that we're talking about. This equation is called the Nernst equation. Now, in order for us to deal with this equation or determine this equation or derive it, I need to introduce to you this equation. Well, actually reintroduce to you because we met this before. Delta G, the standard free energy of a reaction, is equal to the standard free energy change for the reaction plus RT, ln Q. Remember, Q is the reaction quotient, and T is the temperature in Kelvin, R is the molar gas constant, and delta G standard, of course, would be the standard free energy change, and this would be the free energy change at any particular point in time. Now, we already met these two equations here and here. So what I'm going to do is substitute minus NFE for delta G here and minus NFE standard for delta G standard here. When we do that, this would be the result, right? And then we can actually derive an equation where we relate E to everything else by dividing right through by minus NF. So when we do that, we end up with the Nernst equation, which is E is equal to standard E minus RT over NF times ln Q, all right? And again, if we're talking about standard temperature where T is equal to 298 Kelvin, then that simplifies things a bit. We know what R is, we know what F is, so all we have to do is plug those values here, and we end up with this equation here, which is a simplification of this equation. And we also have another form of the equation where instead of L and Q, we have log here. So this equation and this equation are both mathematically saying the same thing. All right. So that's a Nernst equation, which basically helps you to calculate the EMF of a cell based on the concentrations of the substances involved in the redox reaction occurring in a cell. So here's an example based on the Nernst equation. It says, will the following reaction occur spontaneously at 25 degrees if the concentration of Fe2 plus is 0.60 m and the concentration of CD2 plus is 0.10 m. Okay, so this is the balanced equation here. Again, what you have to figure out is the half equations. So for the oxidation half equation, that would be the CD converted to CD2 plus, which would be that. And then for the reduction half equation, that would be the Fe2 plus converted to Fe, which would be that, right? So again, in this case, the number of electrons being transferred would be equal to 2, right? So N would be equal to 2. Now, the standard EMF, we need to figure that out, right? Because, let me go back to the previous page. This is the equation that we're going to use, right? In order for us to determine this EMF of the cell, we need a standard EMF and we need N. We just figured out N. Now we need to figure out the standard EMF. So let me go back to this here. We already figured out what N is. We need to find out what the standard EMF is. So we need to go to the tables and look up the standard EMF for both the Fe2 plus the Fe and the CD2 plus the CD half cell, right? Now, because we know that the Fe2 plus the Fe would be the reduction half cell, that would be the value that we put here first, right? And then we put the value here for the other half cell. So we go to the table and we look it up, and this is what we see. For the iron, for the Fe2 plus the Fe half cell, that's minus 0.44 volts. And for the CD2 plus the CD half cell, that's minus 0.40 volts. So therefore, it's minus 0.44 minus 0.40, and that works out to be equal to minus 0.04 volts. So we have that part of the Nernst equation. So basically, all we have to do now is plug the numbers in. Now, we know what this is. This is the minus 0.04. We know what N is, that's 2. The only other issue is what is Q. And we know what Q is based on what we learned when we were discussing equilibrium. Q is equal to the concentration of the product minus the concentration of the reactants. In this case, or not minus, divided by the concentration of the reactants. In this case here, the only terms that would appear in that equation would be the cadmium and the Fe2 plus, the cadmium ion and the Fe2 plus. Why? Because the iron solid and the cadmium solids are solids. Solids do not appear in that equation. So that's what this part here is all about. We first determine what Q is, which would be the concentration of the CD2 plus, which is 0.10 m, divided by the concentration of the Fe2 plus, which is 0.60. So for Q, we put this ratio here. For the standard EMF, which is minus 0.04, that goes where this is. So therefore, we plug in the numbers into this equation and do our number crunching on our calculator, and we find that this EMF of the cell would be equal to 0.013 volts, all right? So the question is asking, will the following reaction occur spontaneously? Well, because this is positive, what that means is that because it's positive, the reaction will occur spontaneously, all right? Whenever the EMF of the cell is positive, that tells you that the reaction is spontaneous. If it is negative, that means that the reverse reaction will be spontaneous, all right? Okay, any questions about this particular example? Any questions? Any questions? Okay, so just to mention some practical applications of what we were discussing. So if you take any ordinary battery of any type, the underlying principles involved in terms of how these batteries work is what we just covered, actually. So I'm just going to show you a few examples of batteries that we're familiar with from our, everyday experience, working electronic devices and so on. So this is, of course, one of these regular batteries that you, put into, whatever devices that you're using. Of course, you're familiar with the AA size, the AAA size, the 9-volt batteries. Well, this is basically the makeup here. And just to give you an idea as to the type of half reactions that would apply here. So the anode here consists of basically the zinc anode here. This is zinc right here. And that would be in contact, well, with the paste, which is made up of zinc chloride and ammonium chloride. So basically the reaction that will take place, the half reaction that would take place at the anode would be the conversion of zinc to zinc 2 plus by the loss of 2 electrons. Now the cathode would be made up, it's a bit more complex, would be made up of manganese 4 oxide. And basically the way this works, well, this is a half reaction here in that case. So basically it would be the ammonium plus the manganese 4 oxide plus 2 electrons to give these products, right? So this is the anode reaction, the oxidation reaction. This is the cathode reaction, the reduction reaction. When you add these two together, you're going to end up with the net equation, right? And that's basically how this works, all right? So that's what we call the dry cell, also known as the Leclanché cell, right? So that's just one example. Here's another example. Now, this one is called the Mercury Batteries. You tend to find these in watches and calculators and so on. And in this particular case, the anode is made up of zinc, which is the surrounding material here. The cathode is made up of steel. And there's a paste electrolyte solution mixed with zinc hydroxide and mercury 2 oxide. So I'm just showing you here the two half equations. Again, you have oxidation taking place at the anode, reduction taking place at the cathode. When you add these two half equations together, you're going to end up with the net reaction being what we have here, all right? And then we have another example. Now, this is the one that is, of course, you would see in your motor vehicles, in your cars. This is the lead storage battery. As the name suggests, it consists of lead, which in this case is acting, actually lead 4 oxide, which is acting as the anode in this case. So this is the anode reaction taking place as far as the lead is concerned. Actually, the anode is made up of just lead, not lead 4 oxide. So that's the anode right here. And then the cathode is made up of lead 4 oxide, all right? And these are the half reactions, again, taking place. Of course, the net equation would be the sum of those two. And this would be the resulting equation for the reaction, which produces the electricity in this type of battery, all right? So these are just some examples of batteries that are in everyday use. And the underlying principles is based on what we were discussing earlier in this particular chapter. All right, so with those examples out of the way, now we're going to get into the second part. Oh, I'm sorry, there's one more example right here. This is known as a solid state battery. In this case here, these are the two half reactions consisting of lead as the anode, and the cathode is made up of titanium 4 sulfide. And as you can see here in this case, these are the half reactions. So basically to get the net equation, to get the net equation, you simply add this equation to that and you get your half equation or your entire equation. Okay, so here is one which is not in, last I read about this, people are still working on this in terms of using this for regular purpose. But I think there's some kinks in terms of, bringing this to market. This is called a fuel cell. And I think part of the problem why this is still not ready for use by the wider public is this statement right here. It requires a continuous supply of reactants, the reactants being hydrogen and oxygen, right? So basically what we have here is an anode, which is an inert material, which is in contact with the hydrogen, and another inert material. I think if I'm not mistaken, the anode and the cathode, the inert material is, okay, I was about to say graphite, but it's actually a mixture of graphite and nickel, all right? So basically at the anode, this is a reaction taking place. Hydrogen reacting with hydroxide, which is provided here, by the way, a hot solution of potassium hydroxide to form water, and electrons will be lost, and those electrons will enter the external circuit to power whatever device you have here. The electrons will enter the cathode, And at the cathode, you're going to have the reaction between water, oxygen, plus the electrons to form the hydroxide ions, all right? So that's the oxidation reaction taking place at the anode. This is the reduction reaction taking place at the cathode. These are the two half equations here. And when you add them together, basically, you're going to get the combination of hydrogen and oxygen to form water. Now, this would be, if they can get this working, this would be really nice because the product of this reaction is environmentally friendly, right? It's water. I mean, it won't harm the environment. But there are some issues, as I said before, in terms of getting this to work so as to be commercially viable. As I said before, one of the problems is that you need to have a continuous supply of hydrogen and oxygen running into this system in order for this reaction to take place. And another issue, if I'm not mistaken, is the fact that you need to have a hot solution of potassium hydroxide so that this reaction will take place. So if those issues can be overcome in this particular case, then this would be a very environmentally friendly form of energy source that can be used, all right? So here's hoping that they can work this out. Okay, so those are just some examples of batteries, all based on the principles that we were discussing earlier. Another application of what we were discussing is in the whole idea of corrosion, right? Certain metals, including iron, if left exposed to the atmosphere and to moisture, will undergo rusting, right? Rusting is basically the formation of rust. Rust is a compound resulting from the combination of iron and oxygen to form, excuse me, to form iron 3 oxide, which is, excuse me, rust. I don't know where that came from. Anyway, so the diagram that you're seeing here is basically demonstrating how that happens. So let's say you have your, iron metal here. One part of it will serve as the anode. The other part will serve as a cathode. So at the anode, what happens is that the iron metal is eventually converted to Fe3+. So firstly, it's converted to Fe2+ by the loss of 2 electrons, and then the Fe2+ formed in the first step loses another electron to form Fe3+, right? At the cathode portion of the metal, you have basically the electrons that is lost from the anode reacting with oxygen and H+ to form water, all right? The oxygen, of course, comes from the atmosphere. So basically, that's what happens. And then what happens further is that the Fe3+ reacts with the water to eventually forms rust. So that's basically how rust is formed. It's actually an electrochemical process which is responsible for the formation of rust. Now, we can actually combat corrosion of this type by applying what is known as a sacrificial metal. So the example, the way this works, so let's say you have an iron storage tank that you want to preserve, all right? So it's subject to rusting, of course, again, because of exposure to the atmosphere and moisture. So in order to prevent that, what you can do is connect that iron storage tank to a piece of magnesium by a wire, all right? And the way this works is that you're going to have two potentially competing reactions taking place. One of which would be the conversion of Fe, hold on 1 minute. One of which would be the conversion of Fe2+. Let me write this equation down. Hold on. Okay, I'm sorry. So one of which would be the conversion of Fe2+ to Fe3+. All right. In fact, okay, let me do this here. Let me erase this here. I'm sorry. I think I made an error. Erase this here. Okay, so it would be Fe converted to Fe3+. plus 3 electrons. Now let me look up the standard EMF values for those two reactions. So to go from Fe3 plus, from Fe to Fe3 plus, according to what I see here, the standard EMF value for that would be equal to minus 0.04 volts. And for the magnesium to magnesium 2 plus, according to the tables, the standard EMF value for that, write it here, E0, would be equal to plus 2.36. All right. Now here's the thing. Obviously, 2.36 volts is larger, more positive than minus 0.04 volts, right? So what that tells me is that in a competition between these two, this reaction here is more likely to occur. So when you hook up the, go back to my pointer here. When you hook up the magnesium by a wire to the iron storage tank, instead of the iron undergoing the oxidation, it is the magnesium that will undergo the oxidation. So therefore the iron, which makes up this tank, will be preserved, and therefore it will not rust, right? And of course, if you're storing water in it, then that would be okay. That is what you want. You don't want the water to be contaminated with any rust or any Fe3 plus, all right? So basically, we use magnesium as a sacrificial metal in order to protect the iron storage tank, right? So we call this the cathodic protection of iron, of the iron storage tank, because basically we're using the magnesium as a sacrificial metal to undergo oxidation so that the iron will not, and therefore the iron storage tank will not undergo rusting. So that's just one simple application of what we have been learning so far in this chapter. Okay, so now that we have talked about cells and all of that, that's the first part of our discussion in this chapter. The next thing we're going to talk about here is electrolysis, which is basically using an electric current to drive a non-spontaneous reaction, right? So what we were discussing before, when we were discussing galvanic cells, we were talking about using a spontaneous reaction to produce electrical energy or an electric current. What we'll be talking about here for the rest of this chapter is using an electric current to drive a non-spontaneous reaction. So what you're looking at here are two examples, one industrial and one in the lab, of an electrolysis process. The one to the left is what is observed very often in industry. So let me try to describe what is happening here. What we have here is sodium chloride in a liquid state. In other words, we call it molten sodium chloride. Of course, to get sodium chloride in a liquid state, because it's ionic, it's normally a solid with a high melting point under normal room temperature conditions. So you have to heat it to a very high temperature to convert this to a metal, right? Now, convert it to a liquid or the molten state. Now, if it's a liquid, what that means is that in liquid sodium chloride, you're going to have free ions moving around, sodium ions and chloride ions being very mobile, moving around. Okay, so I just thought I should make that clear before I describe the rest of this setup. So for the rest of this setup, what do we have here? We have electrodes. We have cathodes here, right, which will be connected to an external circuit, and we have an anode here, right? The anode would be positively charged, and the cathode would be negatively charged. So what's going to happen is that the sodium ions, which are floating around, will be attracted to the negatively charged cathode, right? And reduction is going to take place at the cathode, right? So the reduction equation is what you see here. The sodium plus the electrons will give you the sodium metal, right? And the sodium metal will actually, sodium in a liquid state will be guided by this pipe right here. And the same thing is happening here. So these are the two cathodes where you're going to have the sodium ions undergoing reduction. At the anode is where oxidation will take place. And that's represented by this half equation right here, where the chloride ion will lose electrons to form the chlorine gas. So you see here, chlorine gas being formed, all right? So that's basically what will happen as far as the electrolysis of molten sodium chloride is concerned. And this is showing you basically the same setup. This is a molten sodium chloride, and oxidation will take place at the anode, reduction takes place at the cathode. This is your electricity source, which drives the reaction. And these are the two half equations, as I said before. So of course, if you add this equation to this equation, the resulting net equation, let me write that down here. The resulting net equation would be 2Cl minus plus 2Na plus to give NaCl, right? Now, normally, this would be a non-spontaneous reaction, right? You won't have, if you add two solutions, one containing chloride and one containing sodium ions, you will not have them coming together by themselves to form sodium chloride in the liquid state. Whoops. Right? So in order for you to force that reaction to take place, you need to provide energy. And that energy comes from the battery, which is a part of the setup right here, right? So that's how the non-spontaneous reaction is driven, all right? So that's what happens in the case of sodium chloride, and basically that will happen pretty much for any ionic compound in a similar situation, all right? Now, let's look at what happens in the case of the electrolysis of water. It's the same setup. The only difference is that now here we're going to have a dilute solution of sulfuric acid, right? So what is going to happen in this case? Well, what happens in this case is that at the anode, as we said before, oxidation will take place, and the substance undergoing oxidation will be the water, right? The water will undergo oxidation to form oxygen gas and H+. At the cathode, reduction is going to take place, and this is the reaction right here. So basically, in this case, the reduction will be where the H+ ion combines with electrons to form H2, all right? So that's what happens in the case of the electrolysis of water. Now, you might be wondering, why is it that we use a dilute solution of sulfuric acid? And the answer really is that the sulfuric acid provides a higher concentration of H+ ions and allow for electricity to be conducted in the aqueous solution. If you had used pure water, the same reaction would take place, but at a much slower rate, right? Because in pure water, the concentration of H+ is lower, right? But if you just add a small amount of sulfuric acid, the reaction will take place more quickly, and that's because the concentration of H+ is higher if you add sulfuric acid to it. So what you'll find is that, well, before we get to what I was about to say, if you add these two equations together, let's see what the resulting equation is going to be. So let me go back to my pen function. If you add these two equations together, then the resulting, let me see here. Okay, where's my, oh, okay. So the resulting equation is going to be 2H2O to form 2H2 plus O2, all right? And if you look at this equation carefully, you'll see that the products, hydrogen and oxygen, would be formed at a mole ratio of 2:1, all right? And if you look at this experimental setup here, this is the actual experimental setup showing you the hydrolysis, you'll see that the volume ratios of hydrogen to oxygen is also 2:1, all right? So that shows you that the composition of hydrogen to oxygen in water itself is a 2:1 ratio in terms of moles, and in terms of the products, it's 2-to-1 ratio as well when you compare the hydrogen to oxygen. Okay, so that's the electrolysis of water, where we use an electric current to drive the decomposition of water. Okay, now we're going to look at some more quantitative aspects of electrolysis here, right? And the first thing I want to define here is what is known as the charge, right? We can actually calculate the charge based on the amount of current that is passing a particular point in a circuit over a period of time. And this is the relationship between the charge, the current, and the time. The charge is equal to the current multiplied by the time, where the current is expressed in amperes and the time is expressed in seconds, right? If the current is in amperes and the time is in seconds, then the charge is expressed in coulombs. And I remember back in the day when I was a student, I used to minor in physics. And I remember that the symbols that are used for each of these are, let me write it, hold on. Okay, let me write it here. So for charge, the symbol is Q. For current, the symbol is I. And for time, it's T, right? So the way I remember it, Q is equal to IT, where Q is the charge, I is the current, and T is the time in seconds, right? So you may hear me refer to those symbols from time to time, because that's the way I recall doing this. Another thing I want to mention here, remember I mentioned Faraday's constant, 96500 coulombs. That is the amount of charge that is carried by 1 mole of electrons, right? So that's another important relationship that you're going to need whenever it comes to doing quantitative calculations when it comes to electrolysis. So the type of problems that you're going to face in this section is basically outlined in this flow chart right here. So you could be given a problem where you're given the current and the time. Based on those two, you can calculate the charge. And then based on the charge in coulombs, you can convert that to Faraday's, which basically gives you the number of moles of electrons. And then based on the half reaction or the half cell reaction equation, you can determine the moles of a particular substance being reduced or oxidized. And then again, based on the type of questions, if a gas is involved, you can determine certain information about the particular gas, like the grams or liters, whatever. So it all depends on the type of information you're given and what the question is asking for. So just to illustrate the use of this idea, we're going to look at this example right here. And this question says, how much calcium will be produced in an electrolytic cell of molten calcium chloride if a current of 0.452 amperes is passed through a cell for 1.5 hours, all right? So the first thing I would do is try to figure out the equation for the formation of calcium from a molten calcium chloride sample. So I would write down the anode reaction, which would be where the chloride ion is converted to chlorine gas, and then the cathode reaction, where the calcium ion is converted to calcium solid, right? So based on this equation in particular, you see that for every mole of calcium that is formed, there are 2 moles of calcium ions. So that's the first thing I would note here. So this is the net equation. But what I would really want to note here is the relationship between the moles of electrons and the moles of calcium that is produced. So that's a 2-to-1 mole ratio, all right? Now, to calculate the moles of calcium that is produced, what I would do first is take the current and multiply it by the time in seconds. So the time in seconds, of course, you'd have to convert the 1.5 hours to seconds. So this is the setup right here. I start off with the current, which is 0.452 amperes. The unit of amperes is the same thing as coulombs per second, and I would multiply that by the time. So to convert from hours to seconds, this is what I would do. I'll multiply the 1.5 hours by 3600 seconds per hour. And then I would multiply, well, I would first, I would multiply, I'm sorry, by this ratio, which gives you the relationship between the Faraday's constant, which is the charge carried by 1 mole of electrons, right? And then, since I know the mole ratio between the moles of electrons and the moles of calcium, I would multiply by a conversion factor where I would have 1 mole of calcium above as a numerator and 2 moles of electrons below as a denominator. And then you're going to see the units canceling out, as you can see here. The seconds will cancel out, the coulombs will cancel out, and the moles of electrons will cancel out. And when you do your number crunching, you're going to end up with your answer being 0.0126 moles of calcium. That's the answer. They did not specify the units in terms of the amount of calcium which is produced. So you could leave the answer like this, or if you want to convert it to grams, or if the question asks for the answer in grams, then you could multiply this by the molar mass, which would give you the mass in grams, which in this case would be 0.50 grams, all right? So that's basically how that is done. Okay, any questions about this particular example? Any questions? Any questions? Okay, now one last thing, and then that's basically it for this chapter. The corrosion of dental filling is another example of where electrochemistry is at work. Dental filling, I'm not sure they still do this. I remember back in the day, and this was in Jamaica actually, just before I came up here, I had to have some filling being done to my, what they call those teeth, the molars, the one to the back of the mouth. And I remember the dentist that is, he used the Mercury dental filling. I don't think they use this anymore. And in fact, later on, in my case, it fell out and they had to replace it with some other safer filling because there were some issues with mercury and mercury poisoning and all that. Anyway, what I suspected happened in my case is basically what is described in this series of reactions here, where the mercury filling here, this combination here, undergoes oxidation to form the tin 2+, and I think mercury is left behind here, the actual mercury metal. And so that's the oxidation reaction. The corresponding reduction reaction, half reaction, is this right here. So this happens over time, and as a result, can cause pain, which is what happened in my case when the filling came out. To be rushed to the dentist to have that taken care of. So that's just another example. These are some values of the electrode potentials for the different half reactions that will take place in this process. Okay, so that's basically it as far as this chapter is concerned. So what I'm going to do is take another break. And I think what I'll do is look at some questions from the problem, from the assignments. This would be assignment number, what is it? No, assignment number, is it 6 or 7? Assignment number 7. Yes, assignment number 7. So yeah, what I'll do is get you guys started on assignment number 7 when we get back, and then that's pretty much it. In fact, maybe we won't have time to do too many questions because this class ends at what time? 1:10. So in fact, you know what? Let's not take a break. Let's just continue to look at some of these questions. So let me go here, here, and let me go files, and then assignments, and then assignment number 7, which I've published already. Okay, so for assignment number 7, the first couple of questions would be redox. Okay, let's do some redox to start off with. So the first question is this. So I'm going to just go to my writing tablet here and rewrite that equation. So HCOOH plus MnO4 minus to give CO2 plus Mn2 plus. Okay, so what's the first step? Anybody? Somebody?
Split it into two half reactions.
Okay, so what would be the two half reactions?
HCOOH goes to CO2 and MnO4 minus goes to Mn2 plus.
Okay. What next?
You have to balance the oxygens.
Okay, well, actually, you have to balance all atoms excepting carbon and, excepting hydrogen and oxygen, but that doesn't apply here because you have one carbon here and here, one manganese here and here. But you're right, we balance the oxygens. So what does that mean for the first half equation?
You need to add a water molecule to the right side.
Sure about that?
For
the first, you're talking about the first half equation, right?
Yeah.
I would disagree. You know why? Can anybody tell me why I would disagree with that? Why would I disagree with Mr. Muscas? How many oxygens do we have on the left side for the first half equation?
Oh, okay. You just add hydrogen?
Okay, so, well, before we add the hydrogen, so therefore the answer is that we do not add oxygen, right?
Yeah.
Because you have two on both sides.
Yeah.
What about the second half equation? To which side would you add oxygen and how many?
The right side.
How many?
4.
Okay, so 4 water molecules. Okay, so now we're going to concern ourselves with the hydrogens. So for the first half equation, to which side would you add hydrogen and how many? And in this case, we're adding H plus ions.
2 to the right.
Okay, so add 2 H pluses to the right. And then what about the second half equation?
Eight to the left.
Okay, so we're going to add 8 hydrogen ions to the left. Okay, very good. What's the next step?
Adding electrons to both sides.
Okay, so how many electrons would you add to the first half equation, and to which side would you add those electrons?
2 to the right.
Okay, so we're going to add 2 electrons to the right. What about the second half equation? How many electrons would you add, and to which side?
5 to the left.
Okay, so we're going to add 5 electrons here. All right, very good. What's the next step?
Balance the electrons.
Okay, so we have to make sure that the number of electrons lost is equal to the number of electrons gained, right? So how do we achieve that?
Multiply the first one by 5.
Okay, so when we multiply the first one by 5, you're going to end up with 5HCOOH to form 5CO2 plus 10H plus 10 electrons. And then what do we do to this equation?
Multiply by 2.
Multiply by 2, so you're going to end up with 10 electrons plus 16H plus 2 MnO4 minus. So we're multiplying by 2 here. And then on the product side, you're going to have 2 Mn2 plus 8 H2O. All right? Okay, so what next?
Add them together and cancel the electrons.
Okay, so we're going to add these two together. The electrons will cancel out. And then what next? What else do we cancel out, if anything else?
The hydrogen.
Okay, so the hydrogen ions, 10 of these will cancel out 10 of these, leaving behind 6, right? So the final answer will be 5HCOOH plus 6H plus 2MnO4 minus to give 5CO2 plus 2Mn2 plus 8H2O. And then, of course, as always, we check to make sure that all the atoms and the charges are balanced on both sides. So let's do that. In the case of hydrogens, we have 5 times 2, 10, plus 6, 16 hydrogens here on the left. And we have 8 times 2, 16 hydrogens on the right. And then as far as the oxygens are concerned, we have 10 oxygens plus 8. So that's 18 oxygens on the left. And we have 5 times 2, 10, plus 8 oxygens on the right. And then what else? We have manganese. We have 2 manganese here, 2 manganese here. So the manganese are okay. We have 5 carbons here, 5 carbons here. So the carbons are okay. And then as far as the charges are concerned, we have plus 6 minus 2, which will be equal to plus 4. And that balances with the 2 times plus 2 plus 4. So the charges are balanced. And the question says that this is an acidic solution. So this is where we stop, right? Acidic solution. All right? So that's basically how that is done. Okay, I think I'm going to stop here for today. Unless there are any questions you guys have. Any questions? All right, so I've posted, as I said before, assignment 7. So make sure that you take a stab at that. I'm going to post the deadline date for that as well. And hold on, let me check something here. Let me check something here. Okay, so I've also, okay, I just published a portal for you to submit assignment 5, which will be due on the 23rd. And test number 2, that is due on Friday. So make sure that you submit test number 2 on Friday. The deadline is Friday, the 22nd at midnight. Okay, so that's pretty much it. Any questions before I leave? Any questions? Oh, shoot. Okay, so if there are no questions, that's pretty much it for today. So I'll see you guys next class, which will be Monday. All right, so take care. Enjoy the rest of your day. I'll see you next Monday.